Okay, good evening. Thank you very much for coming to my talk. It will not be very mathematical, it will be full of pictures. But just as Professor Kuznetsov did, let me just introduce myself. So I'm a senior professor at Dresden University. It's a technical university. And in the 80s, I was somehow there when all over a sudden a new tiny field of mathematics was invented. And I would just like today to tell the story and a little bit more. And the inventor was my supervisor, but at that time I already was professor, Rudolf Wille. So a few months ago, when we were planning for this visit, for me coming to Moscow, then Sergei Kuznetsov suggested that I should give a talk or should prepare a talk for the Colloquium. And I said, okay, what should it be about? And he said, of course, it should be about your research area, formal concept analysis. And so we took that in the title, but there also was a subtitle called A Useful Example of Modern Mathematics. Well, as I wrote there, a title is a promise. So when then I started to prepare for the talk, I said, somehow I have to address this. So what I have to do today in this talk is to try to convince you that formal concept analysis, very strange word, is useful, modern, and it is mathematics. So that will be what I want to do today in my talk, to address these 3 points. I think that it is an example. Well, okay, that means nothing almost. So the first question, is that mathematics, what we are doing? Oh, there are famous books on what is mathematics. But if you ask mathematicians, I'm a mathematics professor, so I know my colleagues. If you ask mathematicians, most of them have a feeling, but not a clear definition of what mathematics is. And I know that some of my colleagues think what we are doing is not really mathematics. However, the textbook that was shown here, it has theorems, it has definitions, it has proofs, it has many propositions, and some of them are not trivial. So I think that suffices to claim that it is mathematics. It's written in mathematical language, so I think that is enough. I know some colleagues of mine who have papers with whether the addition of these 3 numbers is 0, and they still consider it mathematics, but okay. I think that is enough to argue that what we are doing is mathematics. So let's drop that question and then address the question of if it is modern. And for that question, I have to be a little theoretical, and I will tell you the story how the whole thing began. So I said it is applied theory of lattices as algebraic structures. Now, lattice theory is over a century old. It began in the very beginning of the 20th century. So the paper by Richard Dedekind on, at that time, he didn't speak about lattices, he called it Dualgruppe, dual group. The paper is from 1900, I think September 1900. In the 1930s, Garrett Birkhoff wrote a fantastic book, and he established a new theory which he called lattice theory, and he made it popular. He said it is a smaller or a younger brother of group theory. Well, how many people are on his side, that's a different question. But then many years went by, and then there was a strange situation in the 1980s. In the 1980s, there was somehow a very wild atmosphere in the air of mathematics, at least in Germany, but I think it was in other countries too. We had the feeling that, that we had something to do. Well, you see, that was an end of many things. There was, in the 50s, there was Bourbaki, who invented a new language for mathematics. And people had got accustomed to that. In the beginning of the 20th century, there was Hilbert, who invented the axiomatic method. And then there was the problem with self-contradicting parts in mathematics, which had to be cleared up. And the undecidability discoveries by Gödel. And all this came to a rest and to a point in the 80s, and we thought that we would need something new. And in this atmosphere, at many universities in Germany, there were groups thinking about what could we change. Okay? Later on, I read historians, for example, Herbert Meertens, who claims that this was the end of the modern period, that time, about that time. Well, that's an opinion. So modern, in the opinion of Meertens, ended in the end of the 20th century. So we can say, yeah, it is just modern, what we are doing. Yeah? But it was just at the end of modernity. So we stand in a mathematical tradition with our field. We also stand in a philosophical tradition. So what we asked ourselves in these many, many discussion groups was the question, how can we continue with mathematical research? It made no sense to just have yet another axiom system and make yet some new theorems and so on. It was obvious you could repeat it infinitely, and it would not really be a scientific game. Many people tried to orient themselves at applications. There was the word of mathematization. And our groups was slightly different, and the difference was made in the person of the intellectual leader of the group, of Rudolf Wille, because he was not only a mathematician, he is a very good mathematician, but he also was the member of a philosophy department. I think that is more common in Russia than in Germany. I know many Russian mathematicians who at least have an affinity to philosophy. In Germany, that's quite uncommon. And for example, I had no philosophical education at that time, at least, maybe still. And I was a little bit shocked when Rudolf Wille very carefully started to make us read things like papers by Wittgenstein, Peirce, or Habermas even, and then later by Brandom and modern philosophers. And for me, it was a tremendous experience to notice that that changed our way to do mathematics. I'm not trying to convince you to change the way you do mathematics. I'm not preaching anything here. I'm just telling the story of what we have done. So and I can only bring it to a very simplified point here. So what we felt, what the most important thing was that needed to be added to the way we did mathematics was meaning. What does it mean, what we are doing? And in order to come closer, Wille suggested, on the basis of other authors, a method which then was called restructuring. And restructuring means you should not change mathematics. There are all these wild thinkers and acrobats who do the weirdest and deepest things in mathematics. You should not stop them. They are so productive. But for every field, every now and then, somebody, not everybody, somebody should sit down and tell the story of the field anew in a language that is understandable not only by mathematicians, with justifications that are not internal. We are doing this because we want this and this, because we want to reach certain goals and because it is successful and so on. That is the idea of restructuring. Every now and then, somebody should tell the story of the field anew. And for lattice theory, after 50 years, the time had come to tell it anew. So we sat down and asked ourselves, what do we do when we do lattices? Well, most of you maybe are not so familiar with lattices, but you could ask that in any field, and actually other people have started to do the same thing again for other fields. What happened then when we asked ourselves was that we tried a little bit, and then some new definitions, which were not too difficult, and you will see the very basic ones during my lecture, some new definitions were written down, and all of a sudden the whole group got completely enthusiastic, and out came a very productive time, which still has not finished. And I think the computer needs, no, it doesn't need a moment. Meanwhile, so at that time we were a group of, say, 8 or 9 people. Meanwhile, there are many, many books on the field and so on. So it is an established field of research. And as I claim, also of mathematics. So this is by far not everything. So this volume here, the blue one, the dark blue one, the picture one stands for, I think, now 13 volumes of that series, and many others. The CLA one, some people here are almost ready to start to go to the next CLA conference. This is the one of 2011. There is one in 2015.
Next year it will take place here.
Oh, next year it will take place here. So you could prolong the list considerably. So I claim it is now an active field. Now you want to know what is it. And I like to always to start with that example. Actually, this is an example, so I teach my computer science students mathematics, so they have 4 years of mathematics in Dresden. Let's say now we have moved it, not 4 semesters of mathematics. And usually I start with that example on the first lecture of the first semester. They just come from school. They have never heard anything about lattices, or they think at that moment, they think mathematics is about numbers and maybe functions. And of course, we have to somehow tell them if they study computer science, they will have to learn other things, because functions and numbers are beautiful, but they are not in the heart of mathematics for computer scientists. So we start with that example, and what you see here is real data, well, slightly simplified, from a hospital for patients with eating disorder. You know, anorexia nervosa is, what is the Russian word, you know it? Magersucht? Anorexia. Many young people in Germany have it. It's not funny. You can die from it. It is not known what the medical cause is, so there is no treatment in form of medication, no. Some people say it is more like a disease of the software than of the hardware of the human. And that's where the treatment goes. What I show is a little bit old and outdated, but it makes clear where we are going. So this is from an interview of an anorexia patient. This person is in a hospital, and the treatment is that twice a week she will have a discussion with doctors in a somewhat formalized way, about what he thinks about the people that surround her. And here is part of it. And I have replaced, the person gave values, and I have replaced just the values by crosses. So the questionnaire always included the patient herself, her ideal father, mother, and then maybe other people. So it's obvious what it means, I think. So she thinks that the father is not self-confident, while her ideal is self-confident. That is, the missing cross in the third row, in the third column, for the father, there is no cross, so she thinks the father, she does not give the attribute father, self-confident to the father, but she gives the attribute self-confident to herself, her ideal, and her brother-in-law. Of course, the data sets in the hospital are larger. Now, the doctors, they have a problem. They have these data, they have these interviews. Interview takes an hour. The interview, there is a protocol. Now, if they enter the room of a patient, they have all these protocols, something like 150 pages. They said, oh, if that patient had a flu, an influenza, and had fever, I could look at the curve, and I would see in 1 second what the status of the patient is. Here I have interviews, and I have 120 pages. That's impossible. Give us graphics. So this is the first way of systematically representing the interview in graphics. But it's still not graphical enough. It's a good way to encode the information, but it's not intuitive. So the doctors don't see much here. So, well, I'm now making a little fun of it. So they went to the mathematician and said, can you make graphics from this? And what does a mathematician do? If he looks at this, he says, oh, these are vectors. Because I could read the crosses as ones and the empty cells as zeros, and then every row is a vector in 14-dimensional space, because there are 14 columns. So this is just a cloud in 14 dimensions. Isn't that beautiful? That's a good graphics. Well, doctors are not trained to 14 dimensions, so they prefer if you take a projection to 2 dimensions. And that's what they get. It's not exactly the same data, so it's slightly changed. But that's the typical picture they use in the hospital. And it's the way, what I described is really the way how these pictures are generated. With a certain addition that they try to make the projection informative. And then the doctors take this graphics and say, oh, you see, the sister is between the patient herself and the parents. And that's what they get from this graphics. Now, with the method of formal concept analysis, we would go a different way. We start with the same data, this, and make a completely different picture. And that looks like this. Now, you probably haven't seen such pictures, so let me just take a short moment to read the picture. So you see here 3 things. You see circles, you see lines, and you see words. What a big difference to this picture is in our picture, distance doesn't play a role. So near and far has no meaning here. You could think of these lines being made from rubber, and I could move this point here, and the meaning wouldn't change. What you have to read is up and down. Now you see these little circles, and you see the names of the persons and the names of the attributes there. And the rule is that a person has an attribute in the data of the patient, if and only if you can reach starting from the person, you can reach the attribute by an ascending path. And the little extra rule is, this is not a crossing. Crossings are only where the circles are. Okay, so you cannot change directions here. So it is not allowed to go like this. Okay, that's the reading rule. So let me just try to find, it's easier if I look on this. So what are the attributes of the mother? The mother is on the very right. So you go up and you read that the mother is easily offended. She is apprehensive, difficult, withdrawn, oversensitive, calm, sensitive, ambitious, cordial. She is dutiful and superficial. Because all these words you can reach by going upwards from the mother. She is not attentive, she is not self-confident, she is not chatty, because these words you cannot read from the mother. You cannot reach going up from the point where the word mother is noted. What does it mean? No, let me first say, who is self-confident? Well, you have to look for those persons from which you can reach the word self-confident by an ascending path. Well, that's the same to say as you go down from self-confidence and you see which persons you reach. So from self-confidence down, you get the brother-in-law, you get the ideal, and you get the patient herself. What does it mean that the father is below the mother in this graphics? Well, it first of all means that the father has all properties of the mother. Because you can reach everything which you can reach from the mother going upwards. You can reach from the father you go in the first step, you go to the mother, and then you take the old path. But the father is also attentive, which the mother was not. Because you can reach the word attentive from the father, but not from the mother, by ascending path. So that is the reading rule. What you see here is something which we call a concept lattice. And the study in the mathematical theory and other thoughts about concept lattices is what we call formal concept analysis. And why it has such a strange name will be discussed later. Let me first say, why do I prefer this picture over this picture? Well, for a very simple reason. From this picture, you can reconstruct the original data. Because you can read every cross from this picture. Yeah? You can see which attributes the mother has, and you see these are exactly the ones where you have crosses here. From this picture, you cannot reconstruct the original data. So that means this is a faithful representation of the original data. There is a price for that. The price is that these pictures very quickly get huge and hard to read. And that is a moment when the mathematicians come in and somehow get ideas what you can do to split pictures into parts and so on and so on and so on, to split the structures. Okay, but that was the first reading example of a concept lattice, and now I will show you some more. Before I give you the mathematical definition, they are extremely simple, so that you almost don't believe it. The question is, what is it? Here it is obviously an ordered set, but actually it turns out that it is a complete lattice. But what are these little circles? How do you go from here to here? Well, there are computer programs that do it, but of course you would like to understand what they're doing. So I gave the very basic definitions twice. In the beginning, I give them in words. Usually, I give such lectures to people who are not in mathematics, and they are not so happy if I have a formal definition. Two definitions will hopefully be equivalent. Oh, here we are. So we just formalize, we mathematize two things. The first thing to mathematize is that cross table, the crosses, which you had seen on the first picture. And that's extremely simple. That's just a relation between two sets. So we call that, what you see here, such a thing we call a formal context. And we have two sets. This is a set, here it is the persons. There is a set, these are the attributes. Usually we speak of objects and attributes. So here the objects are the persons. And then we have the third set, the crosses, but that's the set of pairs. So it is a relation between the objects and the attributes. And that is what we have in the definition here. A formal context consists of two sets, objects and attributes, together with a relation between objects and attributes. And if there is a cross, we say the object has the attribute. That's how we read it. And what are objects and what are attributes? That is completely open. You can take whatever you want. There's no condition on it. They need not be disjoint. They can be the same, whatever. You will see many examples. Now, if we have such a cross table, then we can identify certain pairs of sets. And these pairs will have names, so it's not yet written here, okay? So such a pair AB must have the following property. A must be a set of objects, not necessarily all objects, some objects, collection of objects. B must be some attributes, but they must be, in a certain sense, married to each other in the following sense. B consists of precisely those attributes that the objects in A have in common. And A are precisely those objects that have all the attributes in B. And that happens in this situation 14 times. And these were, no, sorry, it was not 14, more. So these pairs of sets we call formal concepts. And they have an order. A formal concept is a subconcept of another one if its first part is contained in the first part of the second. And that is what you see here in this graphics. The white points, much more than 14, they are the formal concepts of that formal context. And the lines give the subconcept, superconcept order, which just has been defined. And you see, we do not claim that these are human concepts, concepts of human thoughts. They are concepts of the special data set we are just looking at. That's why we call them formal concepts. Human concepts are similar, but human concepts are much more complicated. But the similarity between human concepts and formal concepts, they cause the applicability of the theory. Because humans can somehow intuitively work with formal concepts. That's the reason. Now, I show you some examples. In most of the examples, I will not even show you the cross table. I'll just show you the result, because you can read the cross table from the data. This is quite unimportant data. It's stolen somewhere from the internet, and it's probably not true, but it's nice. It was recommended serving temperatures for certain white wines. So the objects here are white wines like Burgundy or Rhone, white Rhone, Gewürztraminer or Moscato. The attributes are temperatures from 6 degrees centigrade to 14 degrees centigrade. And the concept lattice here tells you which wines should be served, or for which wines, which temperatures are recommended by the author of that data set. And you see here's a nice structure, and it's easy to read. It's not so important, as I said. I have the same here for some red wines. And now you may start to get suspicious because you say, well, this is such a simple structure. Can I do some structure theory here? Maybe I have seen that before. Actually, isn't that the same as what I did in 3rd grade in school, or maybe 5th grade? The divisors of 200 is the same picture, right? This is the numbers that divide the number 200 ordered by divisibility. And if you look at the diagram, it's the same diagram. Does that have a meaning? Yeah, it has some meaning. I'm not going into this, is too unimportant for analyzing it. But if another thing is easy to see from the diagram, and maybe even more important here, the diagram has no crossings. It's a planar diagram. Does that have a meaning? Yes, it has the meaning. It comes from the fact that the recommendations are always intervals. So the data does not recommend that you should drink a certain wine at 6, 7, or 13 degrees. They always give an interval as recommendation. And the consequence is that the diagram is planar. That's easy to prove. Yeah? So you see the first ideas, how data and mathematical thought, that's all very, very simple what I said now, but you see the first ideas, how they come together. Here is, again, a very small example. I always have small examples to make them fit on the screen. From linguistics, it's an example from a technique called a semantic mirror. And the mirror here is between the two languages, Norwegian and English. And you know that when you have two languages and you have a dictionary, you know it is not a bijection between the languages. The words do not always correspond. So here we have some words in the neighborhood of good. And so we made a matrix, such a cross table, and on the one side we wrote the authors, it's not my idea, the authors wrote the English words, and on the other side the Norwegian words, and they would make a cross if that was a translation given in their dictionary. And so they get this structure. And it's almost a bijection, but locally it has certain differences. So they group words together, and it's a comparison of the two languages. Okay, let's stand it like this. Still, we are not very close to mathematics, but here it gets a little bit more complicated, but still, in a certain sense, very easy. This is chemistry or archaeology or both. So you are at Nebuchadnezzar's famous palace, and you take the animals. I mean, these, the Russian word for enamel is? Emile. Emile, in German too, emile. So these colors there are the lions, some lions there, and some thrones. T are thrones, and L are some lions. And they measured the amount of metal in these emiles. And again, it is simplified here, so we have only certain degrees, rich and medium and so on, but this was already given by the chemists in the original data. So you see a slightly more complicated structure, but it just has the same method as before. I left out the smallest element, so it is somehow something missing here. There should be one element at the bottom, but it makes the picture too big, so I prefer just to cut it off and leave it out. You see a very irregular structure on the right-hand side. And if you're a little bit trained in such pictures, you see, oh, that's a distributive part. Actually, it's somewhat like the power set. You will see later a power set, and you will see that it looks quite similar to what you see here. And that is true. Such structures that look like power sets, they indicate independence of attributes. Independence means every combination of the attributes can actually show up. And that is what you have on the right-hand side. So the four metals, in a certain sense, are independent. But other things which are not independent are in this part here over there. I took the translation from Google Translate. I don't know if that's correct. I'm ashamed that I don't speak Russian. So there are certain animals. In English, they're called shrews. This is a shrew. It's a mouse. No, it's not a mouse. A mouse would never eat a worm. Mice are not, do not eat worms. So there is something that, you have it here, everywhere.
I've never seen it.
You have never seen one. So the word is over there. And these shrews, so they look like mice, a little bit nicer, and they are certainly in your garden. And they have fleas. And here the very simple diagram shows the shrews that occur in a certain part of Germany, that's southern Germany, and the fleas that are on these shrews. I take this example for two reasons. It's extremely simple, but it's because the data set is so small. First of all, you see that the data set, the picture is not at all tree-like. So you could look at it as a classification of the shrews by the fleas they have. So the attributes here are the fleas, and the objects are the shrews. But in lattice theory, you have a natural duality. You can always turn a lattice upside down by inverting the order. And you again get a lattice. It's called the dual lattice. For cross tables, you have an obvious duality. You could just reflect the table. You could interchange objects and attributes. So indeed, from that you get the dual concept lattice. And that means you have here a double classification. You classify the shrews by their fleas, but at the same time, you classify the fleas by their shrews. So what you take as objects, what you take as attribute, that depends on what you want to do. And that's what this simple example stands for. Okay? My favorite one is the second one, the flea Tarsopsylla octodecimdentata. So it means it has 18 teeth. Yeah, it's so small here, but it has 18 teeth. Yeah? Okay, this was the shrews in Germany. Now I would like to introduce you by one example into a knowledge acquisition technique for which we have a very intense cooperation here, and that's one of the reasons I'm here. And I would like, before I tell you what it is, I'll just show you the example. So what I would like to do is I want to classify certain very simple mathematical objects, namely pairs of squares. Why? Well, first of all, it's such a nice word. Pairs of squares sounds good. Yeah? Actually, what I mean is pairs of unit squares. And I have some attributes by which I want to classify the pairs. So the objects are not the squares, but they are the pairs of squares. Yeah? And you see these attributes we have there, and you need, of course, definitions to make it more precise, but we could go into it if we have doubts about it. So they could overlap, they could be disjoint. Overlap means they have a point in common. Overlap should mean they should have an interior point in common. Disjoint means they should have no point in common. and could be parallel, they could have a common vertex, they could have a common segment and a common edge. Now I start my classification. How do I do that? I just sit down and write down a few pairs of squares, and eventually I come up with this classification. And then I have a problem. Am I done? Is it all? Or are there other examples that would not fit in this classification? So here I took some 9 examples. Actually, down there, that's a pair of squares. They're just equal. Still a pair. Yeah? Sorry. So, is it all? Or did I forget something? And of course, this stands as an example for a much more complicated situation. And here maybe I could do it just by thinking it over. But in more complicated situation, and you will see, hear the news about them, you could not do it by just thinking. So we need a way to prove that we did the complete classification. And here is how I do it. Namely, I look at this picture and I write down the logic of this picture, actually the implication logic of this picture. You can define what that is, and here it is. It's not all implications that hold, it's the so-called canonical base. What does such an implication mean? Let's take the second one, it's short to read. If a pair of square, or if 2 squares have a common line segment, they must be parallel. Yeah, that's a reasonable implication, obviously true. And there are more complicated ones, but all of them are, of course, very easy. Now, the idea of checking the completeness of our example set is these are the implications that the computer deduced by the methods we told to it, from the data. So all these implications hold in all examples you have seen. Now I could try to prove that all these implications hold in general, like the second one. If they have a common segment, they are parallel. Obviously, that is true in general, not only for the examples. So I check one by one if I can prove the implication to be true in general. If not, there must be other examples. And indeed, that is the case. It turns out that these 2 implications are not true in general. And that means I have to come up with more examples. For example, for the first of the 2 implications, I find that if 2 squares overlap and have a common vertex, they need not be parallel. Because you see here, these 2 overlap and have a common vertex. So I must add such an example to my collection. And similarly for the second implication. And it turns out, that's a little bit more thought, that if you do it, then indeed this set of examples is representative for all pairs of squares, and you get a new classification that looks like this. Okay? And this is the technique which can be transformed into an interactive knowledge acquisition method, and Dr. Obietkov and I are writing many pages about that. Yeah. Attribute exploration, that's what we call. Here is a data set in mathematics that was obtained with the same method. Actually, the original data set is much, much larger. So here we have some, I think, 8 or so, or maybe 10 attributes. What are these? These are attributes of lattices. So now we have a concept lattice, but the objects are also lattices. And what I essentially have is the objects are all lattices. And I have these attributes. So lattice could be distributive or modular, or there is a strange property B, which I'm not going into at the moment. And the question is, what can happen? And there were students who did an attribute exploration of some 60 such properties. And they finished it. And how does the result look? You get such a structure, and you get examples. So these are small examples. The objects are lattices. We take representative examples. Turns out that now every implication between these attributes that hold in this concept lattice is true for all lattices. Conversely, for every implication between such attributes that is not true for all lattices, you find a counterexample among these. So we know we have the complete classification of such attributes. That's a technique students really like to do for many, many fields of mathematics. We have already examples. And so this is another description. So we have an expert. The expert gets questions asked, and for every question, the expert has to say either it can be proved or a counterexample can be given. And eventually, we get non-trivial results as you have seen before. Let's make that short. We had a cooperation here. It is just finished. It was based on a PhD thesis by a guy named Peter Kestler, and he did such an exploration for groupoids, and he took identities that groupoids may or may not fulfill. And he took 70 very simple identities, very short ones. I don't go into details which one he took. And he took the shortest possible one, 70 identities. And he did the complete exploration, and the numbers here are not correct. He had to prove many, many theorems, and he had to find 1,400 examples, counterexamples to implications. The lattice that comes out has some 20,000 elements. So it's a horrible idea to come up with 1,400 examples. He did that by hand in his PhD thesis. Now, one PhD student from SAG, from your university, Artyom Revenko, took up that and other problems. It's not the only one. And the idea was to replace Peter Kestler, who did all that work in several years, to replace Peter by a machine. What could the machine be? So in computer science, you find theorem provers. So Peter Kestler had to prove many theorems. As I said, the number 50 is much too small. That's a misprint, but I forgot what the real number is. So couldn't we take that technique and combine it with a theorem prover? And if possible, could we do it even with an example generator? Yes, and Artyom Revenko did that. Unfortunately, it was not easy. So he had to invent a new example generator that was able to generate infinite examples automatically. The usual example generators cannot do it. So what Artyom eventually did, among other things, he completely verified what Peter Kestler had done. He actually found out that Kestler had not made a mistake, but he did that fully automatic. So he built that part of the mathematical theory, the classification of groupoids by these 70 identities, fully automatic, using theorem prover and an example generator. Another PhD student, Daniel Borchmann, built on work of other people, Franz Bader, Felix Distel, Barish Zetkaya, and he used an extension of what I've shown you to a much stronger language. So here we have only implications, but there is a much stronger logical setting called description logics. And he used positive Horn formula in description logics to do the same thing, and he built up the theory, and he can even do it for data with errors. So Borchmann's rather recent thesis is learning terminological knowledge. Terminological knowledge is what is described, for example, in the internet standard OWL. OWL stands for Web Ontology Language. And that's written in description logics. And learning terminological knowledge with high confidence from erroneous data. It's the same technique, but on a much, much higher level. Now, I said I would repeat the original definitions, and here it is. Still very, very simple. So we start with a binary relation between two sets, two arbitrary sets. And then we define two operators, and these are set operators. That is, and they both get the same name. Well, you can make a little difference if you insist on that, but usually it takes too long. So whenever you have a set A of objects, you define A prime to be the set of those attributes that all these objects have. And whenever you have a set B of attributes, you let B prime be the set of those objects that have all these attributes. Every single object in B prime should have all these attributes. And then you get a mapping from the power set of the objects to the power set of the objects, and a mapping from those. So this is from the power set of the objects to the power set of the attributes, and vice versa. And if you iterate it, so you take prime prime, then you're back to the set you started with. You get two such operators that are set operators, and they're both closure operators. And if you are a little bit familiar with lattices, you know that when you have closure operators, you have lattices. That's why concept lattices come up. So where are the formal concepts in this setting? Well, let's define them. A pair is a formal concept of the given formal context if and only if A is a set of objects, B is a set of attributes, A prime is B, and B prime is A. That is the definition. And since we want to speak about formal concepts and about their parts, we call the first part the extent and the second part the intent of the formal concept. So if you transfer that to human concepts, take the concept of a human being. What is the extent? All humans. What is the intent? All properties that all humans have, like being alive, for example. And then we have that order. One such pair is less or equal than another such pair if the first part is contained in the second part. If the first part of the first, the extent of the first, is contained in the extent of the second, and it turns out to be equivalent that the intent of the second is contained in the intent of the first. And if you take all formal concepts of an arbitrary cross table, order them this way, you always get a complete lattice. And actually, there is a theorem, we call that the basic theorem, that describes how you get, in a complete lattice, you need infimum and supremum. You may have heard that. That describes how infimum and supremum can be computed. And there is a second part that characterizes when a given lattice is isomorphic to a given concept lattice of a formal context. And as a result, or a corollary of this characterization, you get that every complete lattice is isomorphic to a concept lattice. So the mathematical theory of concept lattices is the same as the mathematical theory of complete lattices. That's what the theorem says, among other things. Let me just put that into words. So what have we learned from the definitions? There is a natural way of obtaining a complete lattice from arbitrary binary relations. That was already known in the 1930s. Birkhoff has it in his book. There is a natural interpretation as formal concepts. That's what got us nervous in the 80s. That's what was the beginning of formal concept analysis, the discovery that it was so natural. Concept lattices, therefore, can be obtained from all kinds of data, because whenever you have data, you can somehow transform it into a cross table. I just said that every complete lattice is isomorphic to some concept lattice. The lattice diagrams are expressive means of communication, so it's a very, very nice graphics. And eventually, you have an algebraic structure that allows you to compute with concepts. And time is already running, so let me just, in the last 2 points, go a little bit into those and try to give you first ideas how that works. Before, let me just recall the notion of intent and extent. So the white points just stand for the formal concepts. What is it? It's data I got from the airport, from McDonald's. Usually I don't go to McDonald's, but it was 5 o'clock in the morning on the airport. The only way to get a coffee was to go to McDonald's. And in the McDonald's restaurant, they had a table of the allergens that McDonald's products might contain. And the table was essentially a cross table. So I sat there at 5 o'clock in the morning and said, oh, I can make a concept lattice because I have a nice table. And that is the concept lattice. So we focus on, so you see here what happens. I think you can now read that, for example, chicken McNuggets may contain celery and gluten. Everything at McDonald's contains gluten. Yeah, because gluten is at the very top, so from everything you can go up to gluten. I just want to read one formal concept, the red one. You see it? What is the extent and what is the intent? The extent consists of all objects that fall under that concept. So you go from there, you go down along descending path and pick up all names of objects, not of attributes, of objects. So if you go down, you come to chicken burger TS, you come to veggie burger, you come to mac baguette, Thai chicken, mac baguette, beef and cheese, but not mac baguette, tomato mozzarella. That is the extent, these four. And what is the intent? You go up from this point and collect all attributes you find on ascending paths. So that's celery, sesame, milk, and gluten. So the pair of these two sets, that is the formal concept represented by that originally white and now red point. So that is how these lattices consist of elements which themselves stand for pairs of sets. And these are called formal concepts. Okay, so we can't forget about this picture. And I wanted to argue that such diagrams can be used for communication about data. And the example I would like to show you is from a situation with PhD students. It was on a summer school in my university, and they had invited international students. You will see it in a minute. And it was not in mathematics, it was in linguistics. And the summer school was on what they called European keywords. Maybe key concepts would be the better word, but you will just see. They tried to find out what was common between the different European languages and cultures and thinkings and so on for certain crucial words in understanding of the world. And one of the words was Heimat. Now I tried to translate that to Russian, and I found 4 translations. Here they are. That's what Google tells me what the translations, the possible translations of the word Heimat is. In that seminar, the students were asked to give words in their own language that would translate. So here are what the students gave. in different languages. I think you can see what language is meant. And then they started to discuss, and they said, oh, but we have different meanings. So Heimat for a Hungarian student meant something different than for a Bulgarian student. And they somehow tried to find out what it was. And I was invited to the summer school. The students were quite skeptical about a mathematician being member of the summer school. But they had the feeling after long discussions that they somehow need to document the differences. And then I made them fill this cross table. Actually, this is again a small example. We had much more complicated cross tables in the summer school, many. This is only one of many. So they gave some attributes. I do not know the meaning of all the attributes. So what projective means, I do not actually know. But it turns out, oh, sorry for that, that in this example, the cross table is small, the concept lattice is also very small, and it, in a certain sense, has just a planar left-right direction. And the students were able to see this spectrum and to discuss it, and somehow they found that that was a result of their discussion. We could now have a long discussion about the meaning of this, but I just want to indicate that even in areas where people do not know the mathematical definitions, they somehow can get used to the diagrams, and they know very precisely what the individual diagram means. But this technique is not only able to model data, social science, linguistics data, medical data, and so on, but also, of course, mathematical things. Here are two lattices. The left one is the power set lattice of a 5-element set. So it has 32 elements. And the structure is like this. You remember it looks a little bit like the one we had for the animals of Nebuchadnezzar. What I have highlighted with the red dots is one of the two maximal antichains. So you know Sperner's lemma, that the size of the largest antichain in a power set lattice of an n-element set just has n choose n over 2 elements. So here we have 5 choose 2, which is 10. So you find 10 subsets of a 5-element set which are pairwise not comparable, not contained in each other. And these are the 10 here. And there are two such collections of 10 elements. One is the set of all 2-element sets, and the other the set of all 3-element sets. Here you see the set of all 2-element sets highlighted as a maximal antichain. On the right-hand side, you see a much more mysterious lattice. Still a lot of research in number theory about these. This is the lattice of partitions of the number 10. So a partition is a representation of 10 as a sum of positive integers, an unordered representation. And you see that there are, I think, 42 such, I don't know how many points are there, 42 maybe such partitions. And there is a natural order on partitions. It's a certain refinement order, which I'm not going to describe here. And it turns out with that order, the partitions form a lattice, a complete lattice. So there is, as an example, the lattice of additive partitions of the number 10. And I would be very happy if somebody was able to give me the standard cross table in a recursive construction, because I cannot do that. And finally, as the last topic of this talk, I would like to go a little bit in a theory, which is another theory called theory of knowledge spaces. And the reason why I'm going into this, actually you don't have to read all this. The reason is I want just to give you a first idea how the mathematical methodology of formal concept analysis can be used to make more theory in other fields. So knowledge spaces, that's very, very simple theory of learning, which is incredibly successful. Actually, the authors, Doignon, who is a brilliant mathematician, and Fallmanier, they had made software for their method, and they have now sold their company with 200 employees for a price. Nobody knows how much money they got, but Fallmanier donated 8 professorships to his university from the money he got from his software. So what is it? It's about learning. And they have a very naive approach, but it's a good approach, at least for them. They have, an atomistic idea of learning. So think of learning of elementary mathematics. So here you have such an example. You have a learner. It's learner number 11. And the learner has to solve some tasks, some problems. So the atoms in their learning theory are tasks. And they actually have a huge collection of such tasks. So, for example, compute the greatest common divisor of these two numbers, and so on. Yeah? And then we note down which learners can solve which tasks. Well, this is the original data from some publication, but it is too trivial. So I have replaced it by a slightly more complicated thing. So here we have 9 learners and 8 tasks. And let us assume that the learners have answered in this way. This is still only symbolic. In reality, you have some hundreds of learners and you have hundreds of tasks, and you have to deal with them. And of course, you have what the Doignon and Fallmanier have a very nice name for. They have careless errors and lucky guesses. So it happens that sometimes students solve a problem although they are not able to, but more frequently they do not solve a problem although they were able to. That way would be careless error, and sometimes there are also lucky guesses. So the data is usually not as crisp as you have here. Usually there are lots of errors. But let's not go into that for a moment. So from this I could make a concept lattice. So it gives the learners, and you can reach a task if the learner was able to master the task. Well, the concept lattice itself turns out to be not so interesting, but it gives an order on the tasks. And the order is this one here. It is easier than. So it says everyone who has, so H is the most difficult one. E is one of the most easy no, sorry, it's not true. H is not the most difficult one, but H is very difficult. So everyone who has solved H could also solve everything except F. And everyone who could solve G could also solve E. Now, what Doignon and Fallmanier do is they take the downsets. So the sets of elements in this ordered set that have the property that they do not contain an element. That's too complicated. That whenever they contain an element, they also contain all elements below. That are the downsets. So you can think of cutting something at the bottom. And that's what they call the admissible learning states. So if you can solve a task, you should be able to solve all easier tasks. And if you cannot solve a task, you should not be able to solve more difficult tasks. By the way, that was the same. Yeah? So what you can do is you can look at the downsets of this ordered set, and with formal concept analysis, there is just a single algorithm to do that. You get this lattice. This is the lattice of all downsets of this order. There are actually 34 such admissible knowledge states. And once you have that lattice, there is another very simple theory that you can count the linear extensions. I mean, the linear orders that are compatible with the difficulty order here. What is the meaning of such a linear extension? That is a possible sequence of learning all these tasks. Because you should learn the easier things before you learn the difficult things. Otherwise, it makes no sense. If you can do the difficult things, you can do the easier ones automatically. So somehow you have implicitly learned them. So it is easy to derive with a little theory that this has 163 linear extensions. So there are 163 potential ways of learning this. And you see that we now get somehow a combinatorics of learning steps, of learning strategies, and so on. So we are step by step, these were only the very, very first steps, developing a methodology for pedagogics built on that extremely simple learning model of Donning and Farman. Okay, I think that should give you an impression. Thank you for your attention.
Yeah. What was the impact of those anorexia analysis? So how did FCA help solve those anorexia analysis? How did interviewing people help to solve anorexia?
Anorexia, so you are, yeah. Now, at that time, I think the people, it has changed a little bit, but it has not changed completely. I was recently actually have visited such a hospital and spoke to the doctors. At that time, the feeling or the model of the doctors was that the reason for anorexia, or one reason for anorexia, was in the understanding, in the view of the patient, of her surrounding. So the attack to the disease was change the understanding of the patient of her or his surrounding. And the way to do that was to put it all on the table. So they would make long, long discussions with the patient of what she thought or he thought about the person in her social neighborhood. And apparently, very often, just speaking about that would make it possible also to influence that, to make it more open. We have seen examples. I think the ones who made these data, it was not my data I've shown, it's from Norbert Spangenberg and Karl Erich Wolf. They have done some 700 such pictures. And some of them, for the people who were really in bad danger, were horrible. They had an extremely narrow understanding, so there was just good and bad. Extremely narrow understanding of what the people in their social neighborhood would be. I'm certain this is not the only reason, but that was the path of attack to the disease which was used here. They actually have discussed the diagrams with the patients, and the patient was saying, yes, that's what I meant and that's what I did not mean. Yeah? But of course, concept lattice diagrams will not cure anorexia. That's not what I claim. It just gives an impression to the doctor what the situation is.
Yeah, I like this example because typically in data analysis, whenever you analyze anorexia, you must have a set of people who have no anorexia, so you can compare. And here, it's the only technique, in fact, that I have heard of that still can be useful when you have only anorexia people in the data.
So it is, yeah, it is not a comparison of different methods here. That's usually, if you have such data analysis, you have different methods of treatment and you try to find out which is the best. Yeah. And I've heard of several cases here, not of anorexia, but for other things, maybe even more serious diseases that students here study such
I would
data.
ask, also, is this data available at all? This 700?
Yeah, there is. Norbert Spangenberg wrote his Habilitation about it, and I don't know if that ever has been published as a book. I don't know, but the Habilitation in principle can be copied, but it's not
in digital format.
I don't have it in digital.
Yeah, sure, I understand that.
The reason why I'm always successful with the anorexia example for the first semester students is they really get attentive, because everyone knows someone who has anorexia or has had anorexia. Yeah? So they come and say, oh no, we have to learn mathematics, and we start with anorexia, so then I get them.
Other questions, please? Yeah, please.
Oh.
Probably, could you possibly outline the most recent directions of research in FCA? Because through your presentations, it is clear that FCA is a well-founded theory, and probably you could name some challenges in front of that theory, and the new directions of research and the problems we can approach with that. What is still unresolved in this area, probably?
Yeah, thank you for the question. So, research questions in FCA still dominating in FCA are people who are close to data analysis. So there were questions of algorithmicity, complexity. There are some unsolved questions there. For example, I showed you this base of implications. It is still, we still don't have a good algorithm for producing the base. The conjecture is there is no good algorithm, but the final words are not spoken about this. But there are also mathematical things that are under investigation. So a recent result, maybe I cannot name a recent problem, a recent result is, I mentioned that these lattices quickly become large. And the typical example is the power set lattice. And just recently it has been proven that they are indeed the only criminals. So whenever a concept lattice of a small table gets huge, then there is some power set lattice inside. Yeah, that's a typical, say, extremal theory result recently. But there are, we are working on the exploration business. There are now activities on this learning model. There is Boolean factorization that is connected with the learning problem. There is the idea that there should be a reason why some students can solve a problem and some other students cannot. So there is an extended theory of knowledge spaces that works with what they call skills. And skills are abstract things that enable you to solve problems. And they try to find from the behavior of students what skills should be considered. And it turns out that is a mathematical, that can be translated to a mathematical question about factorizations of matrices and so on to find reasonable skill sets. I think there is no automatism. I think that usually the mathematical results will allow many, many solutions, but then in cooperation with the pedagogical view, where they say, oh, we know what skills are there, then you can make precise what the pedagogues think is the theory. Yeah, you can. That's one of the examples as a direction. Does that answer? Could I just add an answer I have not given? My brain is slow. I should definitely mention that there are other groups with other aims also working in FCA. For example, in the Czech Republic, there is a rather strong and productive group that does all this for fuzzy data. So there is already a huge theory of fuzzy formal concept analysis. There is in Poland people who do it for rough sets. There are many Chinese people of which we do not understand what they're doing. Sorry for saying it like this. There are people who think that having objects and attributes is not enough, and you should have more than two dimensions. Well, the founder of the theory, Rudolf Wille, says yes, but 3 is always enough. So there is triadic concept analysis. It turns out that the algebraic structures that are produced are so completely unknown, the tree lattices, that we do not have a good theory of them. Young people apparently like to do research about that because it is so complicated. Yeah? So there are many other activities. I would probably come up with more if I think it over.
What you were saying answers this question. Please.
Despite theoretical beauty of FCA, there is a hindrance with applying it to real data because of exponential complexity of the lattice algorithm. And so what do you know about scaling FCA algorithm? Do they use MapReduce, Hadoop, and PatchSpark, or there are different theoretical foundations for polynomial FCA?
Okay, maybe I repeat that so that the others here, you're already an expert, so maybe I repeat that. So what he was speaking about is the true fact that you have a small cross table and very often the result of the resulting concept lattice is large. Actually, the worst possible case is exponential growth. You can have an n by n cross table and you can have a concept lattice of 2 to the n elements. And that's in a certain sense unpleasant. So there are fast algorithms for generating the concept lattice, but they cannot be very fast because there are so many elements to generate. And he asks if there are tricks to put it into polynomial time, at least different methods. There are people who are working on that. I'm not so much interested in that. My attitude is a different one. I do not think that you have to generate the concept lattice. I made an algorithm how you can do it. But I think usually it's not necessary. So in the usual theory of mathematics in school, the situation is much worse because there are infinitely many integers. But nobody has the idea that before you start addition or multiplication, you first should write down all integers, because you could not even do it. You can do addition and multiplication inside an infinite structure, and you find it completely normal. So the argument that the concept lattice tends to be exponentially large is true, but it does not stop me from going into the concept lattice and computing there. So those questions which can be treated there, these are the interesting questions. And indeed, those questions which require to compute the structure first completely, they have their boundaries when it comes to scaling. Yes, that's true. Yeah?
May I add to the question? Do you see any potential? So you have a real big lattice set.
Yeah.
Do you see any potential if I cannot consider the entire thing because it's too big, but I may consider just the lower side of it, which is smaller. It's a kind of projection, what Sergey is doing. Is it, has it any potential kind of theoretical point of view?
There are many such approaches. One is called the iceberg lattice. So that's where you have the huge concept lattice, but you look only at the top part, and the rest is underwater. This is the iceberg there, and the rest is underwater. And there is an algorithm that computes the iceberg, and you can guess what the name of the algorithm is. Of course, the name is Titanic. So it's the Titanic algorithm that computes the iceberg of a concept lattice. Iceberg for a certain parameter. You have to say what the cut is. But this is only one approach. The other approach is factorization in the sense of factor lattices, sublattices, but the most fruitful one is subsemi-lattices, because factorization into direct products usually does not work. A random lattice is directly indecomposable. That's the experience. And lattices that come from real-world data in general are directly indecomposable, but not as sub-semi-lattices. As sub-semi-lattices. So if you just drop one of the two operations, then they always are decomposable. And that can be used in interactive computer programs in a very simple way.
Well, this is quite interesting approach.
Well,
I never heard of. Other questions? Well, I think this was quite a kind of interesting discussion.
Okay, so I say thank you again, and but before I would like to, I did not say it strong enough, we have an extremely good cooperation. HSE is really one of the highlights, not in following this theory, but in using it for the aims that people here in data science have. So they do not feel like they are in FCA mainly, but they have their aims in data science, and they look if FCA can be useful or not, and if so, then they use it. And we are very happy that that happens, because I'm a mathematician, I'm not such an applied person. I can give you these nice symbolic examples, but in reality and in business and so on, there are much other different standards that are needed, but people here in Moscow, here in this building, they are very clever at doing that, and I'm happy to be in cooperation.
Just one example, Dmitry Ignatov is quite effective in building
collaborations.
How they call this? Collaboration filtering, collaboration filtering system, recommender systems. And in Australia, people do catalogs, and so forth. Okay,
so you are invited to participate.
Thank you.
Thank you.